There we go.
So this is review day, chapter 5 on gases. My thoughts are slow today. I'm kind of drugged. I saw the doctor yesterday and they loaded me up. So I better just take it slow and easy. Any specific problems that you want to deal with before I start doing a review?
I'm expecting a phone call, so I'll get ready for it. But
Yep.
I have it on silent, so.
That's fine.
It will interrupt.
No problem.
Do you want this whole packet or just this?
Actually, all I need is the data pages. Just be sure your name's on it. Okay, so what we can do now is just start at the top, and when when we do a problem, and then we come up to another problem that's the same kind, I'll skip that one. Unless you stop me and want to do it again. So the first 3 questions just deal with memory and definition. Gases generally have what? Well, of all those, the only one that fits is low density. Gases have low density, which is, remember, go back to your definition, mass per unit volume. So when you think of gases, if you have a certain volume of a gas, liquid, and solid, it's going to have a very low mass compared to liquids and solids. So that puts it on the low end of density. Because if this stays the same, and that's very small, then this has to be small. Two, pressure is what? Defined as the mass that an object exerts when at rest. Sorry. That doesn't work either. Pressure is force per unit area. I didn't say anything about mass. The mass has a bearing on force depending on where the mass is. So if a mass on Earth would have a different force or weight if it were on the moon. But when you're talking about pressure, we need force units and then area units in the denominator. So the first one can't be right. It's defined as mass, no. Measured in newtons. Well, part of it is measured in newtons. This one right here is in newtons. But that doesn't give you the area. Pressure is an intensity factor. That means it doesn't change with the amount. Once you define the pressure, then these 2 values are fixed in ratio. They can increase and decrease, but they do so together. So if you increase the force, you have to increase the area. Once you fix the pressure, it's an intensity. It doesn't matter how much you have of it. It's always the same. Whereas this is a capacity factor. Force does change with the amount. Area does change with the amount. But when you ratio them, they become an intensity factor and they don't change. So if you're at sea level, anywhere on the planet, you're going to experience or feel, relatively speaking, 14.7 pounds per square inch. It's the same no matter where you are. If you go to a different altitude, as long as you're at that altitude anywhere on the planet, experience roughly the same pressure, and weather notwithstanding. So C, defined as the number of moles of substance, sorry, moles as an amount is not a force. D, defined as the force per unit area. That's it. It's a simple definition, force per unit area. That's pressure. So we found the right answer. E can't be right. The SI unit of pressure is, what is the SI unit of pressure? Do you remember? The Pascal. And it's the SI unit of pressure because it's defined in terms of, it's defined in terms of fundamental units in the SI system. And fundamental units in the SI system are kilograms, actually, of force. The units are newtons. Let's see. I'll just write it out. Newtons, and then the area is in terms of meters. So it has to be meters squared. So 1 Newton per meter squared is a Pascal. And the Newton is related to Newton's second law of motion. So the force of a Newton is equal to kilograms times meters per second squared. Right? So a Newton then is equal to kilogram meters per second squared. If you need to make a conversion using pascals and your multipliers don't have newtons in them, look for this relationship. Kilogram meters per second squared is a Newton. I don't think I gave you any of those though. That's just information. All these things are related. They're designed to be related. Okay, so that's definitional memory stuff. Now we get to problem solving. So for which of the following would represent the greatest pressure? All right, so now we've got pressures in different units of measure. Okay, so the problem is, the question wants you to compare them, find out which is the greatest pressure, which is the greatest pressure. But it's giving you apples and oranges and limes and lemons and kumquats. You can't compare them this way. They've got to be converted to some common unit of measure. And I think the easiest way is to convert them all to atmospheres, because there's 1 unit conversion for each one. Okay, so this one's already atmospheres, millimeters of mercury. Right, atmospheres. What's the relationship here? 760. Okay. So let me get my calculator out. I could go to the review document, but that would be cheating. And no, that's not my calculator. If I do these calculations each time here, sometimes I find errors. I made a mistake in the review document. That's why I like to do them fresh each time. So this one is 0.680 atmospheres. That one's equal to this one. How about the conversion here? How many PSIs per atmosphere?
14.50.
Mm-hmm. Okay. This one is 0.776 atmospheres. How about pascals? That one you might have to look up. How many pascals per atmosphere?
Well, from the review, it's 1.0,
Let's go to the back and look at useful information. Because you're not going to have the review document on the exam, but you will have useful information. So the relationship, conversion factors, here we go. Left-hand side, down toward the bottom. Pascals. Here we go. 1 atmosphere. 101,325, right?
Where do you see that? Oh,
Toward the bottom on the left-hand side.
I see it, because it says atmosphere, 1 bar, and it has traffic and then passenger.
Yep, those are all equal. So we divide 62,106, 101,325, 0.613 atmospheres. And then the last one, inches of mercury per atmosphere. Remember that one? I think that's in here too. I remember it, but it's better to find it here. About the middle, halfway down the left-hand side. 2992. That's 0.471 atmospheres. Okay, now we compare. Looks like this one is the largest one. Now, that's the answer in this. Yeah, that's the answer. Okay. Black does not want to come off. Okay, let's see. This one's different. A glass column is filled with mercury and inverted in a pool of mercury. Mercury column stabilizes at 725 millimeters. What's the pressure of the air? Well, we've already done conversions. The same type of conversion. You're just converting millimeters of mercury to atmospheres. Right, so we've already done that kind of problem. Let's see, how about 6? Local weather forecaster reports 30.4 inches of mercury. We've already done one like that. A physics experiment is conducted at a pressure of 14.4 kilopascals. What's a kilopascal? Kilo means 1,000. So the unit of measure is 1,000 times a pascal. What's the pressure in millimeters of mercury? Right, we'll do this one because there's a slight twist. So we're given 14.4 kilopascals, right? Which means how many pascals? Right? Move it 3 to the right. 1, 2, 3. Why did I move to the right? I'm sorry?
Okay.
Right. From this unit to that unit, this is larger, it gets smaller. So this is smaller, it's larger. That helps you know which direction to move your decimal point. Now that we know that, we can use our conversion factor. Which was 101,000 something, wasn't it?
101,325.
So it's going to be more than an atmosphere. Wait. No, less than atmosphere, excuse me. Because that's smaller than this. So it should be. Oh, no, that's 14,000. Yeah, it's going to be a lot less. I was mentally adding another zero in there. Taboo. There we go. Yeah, 0.142. Let's see, 7. Oh, millimeters of mercury. Okay, so we've only gone part of the way. Right. Now we got to get rid of the atmospheres. There we go. Now multiply that times 760. Let's see, 108. See if that fits. Yeah, D, 108 millimeters of mercury. Okay. Always helps to go back and look at the question every once in a while. Okay, that was 7. Air pressure in the inner tube of a tire, 112 psi. That's true. I used to have. I didn't have a racing bike, so that's really high pressure. But I did have a 10-speed, and I think I kept the pressure at 80 psi, which is pretty high. What's the pressure in your car tires? Do you know? Mine's 35.
Mine's, I think,
40? Okay.
40 to 44.
It's a smaller tire, isn't it? What's that? You drive compact?
No, I have SUV.
SUV, okay.
I think it's 40 to 44.
Okay.
If I have I think it's 16.
Okay. Yeah. So I imagine those people that have those 18-inch rims with the little narrow tires, they're probably up to around 50 or 60 psi. Smaller the tire, higher the pressure. Okay. Convert this pressure to atmospheres. We don't need to do that. We've already done one just like that. 2 more definitions. Boyle's law. First of all, what's Boyle's law in formula form? Right. Pressure times volume equals a constant. Or P1, V1 equals P2, V2. Okay. Now, this is Boyle's law in words. So we got to make sense of the words. Equal amounts of gases occupy the same volume at constant temperature and pressure. That's not Boyle's law, is it? Amounts of gas. Doesn't say anything about amounts of gas, except, of course, we know that temperature and amounts are constant. Right? Remember the 4 factors? Pressure, temperature, volume, and moles. Those describe a gas. So if you're going to let these 2 change, you got to hold those 2 constant. Right? So A is allowing this one to change. It can't be Boyle's law. Right? The volume of a fixed amount of gas is inversely proportional to its pressure. Fixed amount of gas, constant temperature. That's what that one says. And then it defines the relationship between P and V. What we have to do is to say inversely proportional. are they inversely proportional? Right? So you can do it two ways. You can graph it like that. It has a negative slope, inverse proportional. Or if you know the rule of thumb, products equal a constant, always inversely proportional. Okay. While we're on the topic, what relationship is directly proportional when you have two variables multiplied equals a constant? Two variables in some sort of ratio is equal to a constant. Quotient equals a constant. That's direct proportion. Product equals a constant, inverse proportion. Okay. Oh, that's the answer. B. We don't have to go any further. So we'll go to 10. This is Avogadro. What was Avogadro interested in? Avogadro was interested in the change in volume with a change in number of moles. So that one is a direct proportion. A quotient equals a constant, direct proportion. It would be graphed like that. Now let's look at our choices. Equal amounts of gases occupy the same volume at constant temperature and pressure. Okay, this is a modification of Avogadro's law. And it's based upon this premise. If you have two volumes of gases, doesn't matter what they are, gas is a gas is a gas. We're talking about ideal gases. If you have two volumes, and this volume and that volume are equal, okay? And the temperatures are equal, and pressures are equal. And this is inside, this is where the gas is, temperature, pressure, volume, all equal. And Avogadro says moles are equal. Exactly the same number of particles in this one as that one. That was Avogadro's revelation that we didn't have time to talk about it, but there was this big conference at the university in Karlsruhe, Germany in 1865, I think it was, or 4. They were trying to figure out why their reactions were going wrong and they didn't know how to fix them. Right? For university professors, that was just a blotch on their reputation. But for companies and their chemical engineers, it was costing them lots of money. So they had to figure this thing out. They had this big conference for a week or two, and they all just threw up their hands and walked out. Said, I can't figure it out. Fortunately, there was this guy, a young scientist named Cannizzaro, another Italian. He had taken Avogadro's work and developed it. He was handing out his reprints as they were leaving the meeting. They all took them back to their cities and their companies and their universities. Some of them read it. Light bulbs started going on all over Europe. Figured it out. It had nothing to do with the mass. They were all focused on mass when they were reacting, doing reactions to products. What they needed to focus on was moles, numbers of things. That's why now when we write our equations, it's in terms of moles, 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 moles. When we do our stoichiometry, you can't get anywhere in a reaction without moles. It's got to be numbers of things. You can convert interchangeable with mass, but you can't do it until you get to your destination. That's how they solve the problem. So we give Avogadro credit, but the footwork was done by Cannizzaro. And it was based upon this relationship. Now they knew that if the number of moles were equal between these two and they had two different gases at different masses, so if you have equal number of particles in each side, the only way they can have different masses is each one of the particles has a different mass than the other one. Then they could relate individual atoms, molecules, whatever the case may be, between the two. It was huge. And from that point on, basically Germany ruled the chemical world for quite a while, several decades. If you wanted to study chemistry when I was in high school, you had to learn German because that's where all the publications were coming from. Now, most of the publications are either in English or they're translated into English. So German's not a requirement anymore. Okay, so that's the answer. A. A answers that. Okay, 11, Charles' law. I hate when they do that. It used to be when you wanted a possessive, when you turned a word, a noun, into a possessive. If it had already ended with an S, you just put one of those at the end. You know, now I guess somebody decided that we can't do that anymore. You have to add an S. Charles's law. I still like that better.
It sounds better.
Yeah, Charles' law. Okay, so what does Charles' law state? Well, Charles is a relationship between volume and temperature. So pressure and moles are held constant. So we have volume temperature equals a constant. Direct proportion, right? Positive slope. So let's see which one of these fits. Equal amounts of gas occupy the same volume. No, that's Avogadro. B, the volume of a fixed amount of gas is inversely proportional to its pressure. Volume and pressure is Boyle's law, not Charles. The volume of a fixed amount of gas, okay, fixed amount, that's right, is directly proportional to its temperature. Volume and temperature, that's good, in Kelvin at constant pressure. Constant pressure. That's it. That's Charles' law. C. Cough all over everybody. Okay. Let's see if this one's different. Consider a sample of helium gas in a container fitted with a piston. Okay. We got our piston, and it says that there's 10 kilogram mass sitting on top of it. Okay. How many of the following processes will cause the piston to move away from the base and decrease the pressure? Okay, so the conditions they're giving us here, we have to say, has to do that, piston has to move up, and pressure has to go down. Which is what will happen. If the piston goes up, the pressure has to go down because the amount is fixed and the temperature is fixed. Well, actually, that may be one of the changes. Let's see what the changes are. So Roman numeral 1 says, oh, by the way, this is helium. Heat it. What happens when you heat it? goes up. Well, what happens to the pressure? Pressure, well, okay, here's the key. What is the pressure on that gas? It's that kilograms plus atmospheric. Pressure doesn't change, it's fixed. Right? So heating the helium will do this, but it won't do that. So that doesn't work. Remove some of the helium from the container. What happens if we're back to square one now, you take out some helium. What happens? The piston drops, it doesn't go up, right? And the pressure stays the same. So based on, not that one, but this one, let's see. Remove molds. That doesn't work either. Okay. Turn the container on its side. What if you turn the container on its side? How is this exerting pressure on that piston? Gravity's pulling it down. Turn it on its side, gravity's pulling it down, and there's nothing pushing sideways. So you decrease the pressure with this. Decrease the pressure, increase the volume. That one works. Decrease the pressure outside the container. Decrease P outside. So how would you do that? Well, if we set it back up the way it was to start with, you still got this pressure, but the total pressure here is equal to the 10 kilograms plus atmospheric. So the only way you can decrease the pressure on the outside is to decrease the atmospheric. Stick it in a vacuum chamber and remove air from around it. So that being the case, what would happen? Decrease the pressure. You know what? This one is true. See, I found an error. Let me look at my explanation and see if I've got there's no explanation. I'll skip that one. Okay. So I think that the answer should be changed to C, because both 3 and 4 answer the question, unless you have an objection or question. Does that make sense? This one is easy to figure out, because when you turn it on your side, the 10 kilograms is not pushing anymore. So you have decreased the pressure, and with decrease in pressure, the volume is going to increase. I mean, that's what Boyle says. But here, if you decrease the pressure on the outside, you still got the 10 kilograms. Still got the 10 kilograms, but if you decrease the atmospheric pressure, then you decrease the total pressure, and the same effect is 3. So that's why I think.
Should be 3 and 4.
Yes.
So both of them were correct. So if we have a question like that on our exam, one or the other, we're talking about.
Yeah, if that question is in the test, something like it, right, then I'll accept both of them. You'll probably have to remind me. Okay. Let's see. Gas sample is held at constant pressure. Gas occupies volume, temperature 21.6. Determine the temperature of the volume. Okay. Let me work this one from scratch. What are we given? A gas sample is held at constant pressure. Pressure is constant. Sometimes it helps. Actually, it always helps to take these word problems and extract the information that's given. Pull it out of a word problem, because word problems are designed to confuse. What they're testing is, do you really understand what's being asked? So they do that by confusing. They just throw a bunch of stuff at you. It's kind of like a cheetah chasing a herd of antelope. They're running all this direction that they're confusing him, and it's on purpose. Try to confuse the predator so he can't catch you. Can't catch anybody. So with these confusing word problems, extract the information that's given first. Then go to the question and see what's asked, and then you can look at the information and see if you got enough. So that's constant. Gas occupies 3.62 liters of volume. And the temperature at that volume is 21.6 degrees centigrade. Okay. Determine the temperature at which the volume of the gas is 3.42. So we've got a change in volume. This is one volume, and this is the second volume, 3.42 liters. And the question now is, determine the temperature at which this occurs. So these are related. These are related. Okay, and the question is, what's that one? Now we've got everything up there. We say, okay, we need to solve for this one. What relationship is volume to temperature? Whose law? Charles. So we're saying that V1, not times, V1 over T1 equals V2 over T2. Now that you've got the information correctly written, you got the formula that applies, all the thinking's done. You just plug in the values and solve it. Okay. Or we can solve it first. So bring this one over here, these two go over there. All right, check my algebra. Then we can plug it in.
Since we know we have to use Kelvin, can we go ahead and change the 21.6 into Kelvin?
Yes. Okay, so V2 is 3.42 liters. T1 is, let's see if I can do this in my head, 294.6 K. And then V1 is 3.62. I just crunched the numbers. 294.6. I get 278 K. Now we have to look at the answers and see, is it in K? 13? Yes, the answer's in K. So you can just find which one fits. Looks like it's B. Sometimes the answer will be back in centigrade, in which case you have to subtract 273. Or if I'm really evil, I'll put all the answers in Fahrenheit. Then you have to convert to C in the Fahrenheit. But that way of solving these problems, I think, is useful. because of the nature of word problems, you've got to extract the information out into a form that's visible. Then it's easier to figure out what the answer might be. That was 13. Let's see. 115. Yeah, we've only got a half hour left, so I'm going to have to skip some of these and move down to, use this. Let's see what 20 looks like. Thought problems, they're the ones that have a habit of giving students trouble. So 20 says, you've got two balloons, an orange and a blue. So I don't know what size they are yet. This one's orange. This one's blue. Okay. The orange balloon is filled with neon. And the blue is filled with argon. Okay. The orange balloon has twice the volume of the blue. Okay. So this one is going to be twice as big as that one. So that's volume of neon. This is volume of argon. And this one is twice the size of that one. So that means this one equals twice that one. Okay? Which of the following best represents the mass ratio? So we're looking for what's the relationship of the mass of neon to the mass of argon. That's just how are they proportional? That's the question. Okay, let's look at our choices. The pressure in the container doubles. No, wrong question. Sorry. What's the ratio of the masses? Well, let's look at it this way. If all things being equal, pressure, temperature, we know the ratio of the volume. So Avogadro's law says that the volume and the moles are related this way. Right? If you increase the volume, you have to increase the moles. Right? So if we're going to double the volume, we have to double the moles. Right? So we know now that the number of moles of neon is twice the number of moles of argon. Did I lose you yet? Avogadro says if these were both the same volume, they would have the same number of moles. But this one's twice as big as that one, so it has to have twice the moles of the argon. Okay? So twice the moles, we know that now the number of moles of this one is twice that one. Now what's the ratio of masses? Right? So how do we get mass out of moles? Right? If you have the moles of something and you want to convert it to mass, you need.
Wouldn't neon have the two?
No.
Twice the volume.
Here's the ratio. If you want to find out what neon is, you have to double argon. Okay, that's why the 2 is in front of argon. That always used to give me trouble too. See? And the reason I finally decided to drill it into my head was I always got the wrong answer when I tried that. Right? It was actually, I got the 4th of the answer. Because it's 2 this direction, 2 that direction. I missed it by a 4th. So if you look at it this way with a picture, you see that if we know the volume of this, to get the volume of that, you have to multiply that one times 2. Okay. So now that we know that, if you want to find the number of moles of something, you need the molar mass, grams per mole. Right? So grams per mole. All right. So what are the grams per mole for neon? About 20. Right? And for argon, it's about 40. Okay. So if we ratio these to say, the question says the ratio of neon to argon. So we want to know the mass of neon ratio to the mass of argon. That's the order. So to convert those, we need to convert let's see. I'll be sure I put this up there right the first time. Let's do it different direction. We want neon on top, argon on the bottom. So if we divide both sides by like that, now we've equal 1. We got this ratio. Now that we've got that ratio, we can convert the ratio to mass from here. So yeah, let's put it over here. Moles of neon per 2 moles. Now we can convert each one to mass. So mass on top for neon is 20 grams per mole. That cancels this and this. And 40 grams per mole. It cancels. Actually, it cancels both of them. So we have 20 per 40 equals 1 to 2. Neon mass, argon mass. So it should be 1 to 2. Now it says 1 to 1. Why is it 1 to 1? Oh, duh. My mistake. It doesn't cancel the 2. It only cancels this part. So, okay, I know it's a little confusing. Actually, it's a lot confusing because it didn't work that way.
So I think the grams supposed to be on the bottom and the mole on top, and that way the 2 divided by 40 would be 20, and then it would be 1 to 1.
Let's try it rather than using algebra. Let's try it from a purely logical form. If argon is 40 grams per mole and neon is 20 grams per mole, if we have twice as much neon, its factor is going to be twice this. So they're actually equal. We went 2 this direction, we're going 2 that direction. So that's why they're 1 to 1 mass. That worked out better?
Yeah.
Yeah. I think I overcomplicated it. The key to this one is recognizing that you have twice as many neon as you do argon. but each neon weighs half as much as the argon, so they're actually equal. Okay. I'll run out of time. I want to be sure I get to all the important stuff. How about 23? In which flask are the molecules least polar and therefore most ideal? Oh, that's referring to the situation above. So 23 is referring to the basic information above, which is we have 3 flasks, 1 liter each. This one has ammonia. This one has nitrogen dioxide. This one has nitrogen gas. This one's A, this is B, this is C. Okay, those are given. Now 23 says, in which flask are the molecules least polar and therefore most ideal? So you're actually told there that the least polar molecules are the most ideal, that is, they behave ideally. Why is that? Well, remember one of the conditions of an ideal gas is they don't interact. When they meet one another, they don't attract, they don't repel. So you're more likely to encounter ideal behavior when you have nonpolar molecules. Because what happens with a polar molecule? Whatever your molecule is, if it's slightly positive on this side and slightly negative on that side, when they encounter one another, if they encounter one another like this, there's going to be attraction. And that screws up your ideal behavior. Right? So you don't want polar molecules if you are expecting ideal behavior. Right? That's why we're going for the least polar. So what you need to know is, how do you tell polarity in these molecules? Well, we haven't got there yet. So I just have to tell you, ammonia is a polar molecule. Nitrogen gas is nonpolar. And nitrogen dioxide is a polar molecule, simply because it has an imbalance of electron distribution, which means these two up here, mean this side of the molecule is slightly negative. So down here is slightly positive, is polar. Similar here, actually, there's a competition between these two and that one. But this one is polar also, simply because of the difference in charge plus its bent. This one is nonpolar. You can tell because nitrogen, they're both pulling on electrons the same, because they are the same. This nitrogen has an attraction for electrons. This one has an attraction. They're equal. So they balance, and the whole molecule is nonpolar. So this one is the one that will behave most ideally. Almost a lot to take in right now, because we haven't got to the discussion of polarity yet, have we? No, I didn't think so. So if a question like this pops up on the exam and you need to know polarity, just ask me and I'll tell you. I think I've tried to eliminate that type of question. This is instructive, but a little ahead of the game right now.
Well, it's kind of easy if you think of like polar, non-polar being the same and not the same, or they're the same.
Yeah.
Non-polar.
Yeah, figuring out which one's polar and which one's not is the trick. Let's see.
least those two would be non-polar.
Right. In fact, all the diatomic gases are nonpolar for that reason. Like hydrogen, they're all nonpolar. Of course, these are single atoms, so they're definitely nonpolar. Right, all the noble gases would act ideally up to a point. If you decrease the temperature far enough, then they start interacting. But we haven't got to that discussion yet either, so we'll save it for another day. Let me see. I want to be sure we're covering everything. How about, let's see if this one's. How about 30? If you remember, when I was talking about types of gas problems, you can subdivide them into two types. There's what I call before and after. And then there's the state. This is where you know conditions before and you change the conditions for after. Use a set of solutions for that one. The state function is one where you're just given the conditions right now. What do you do with it? Right? There's no change indicated. Right? So with these, you use variations of the combined gas law. So you have pressure, volume, moles, and temperature. Then, of course, if you hold any of these constant, like you hold moles constant, so to do that right. Yeah. Hold the moles constant, then you don't have to deal with those. If you hold these two constant, you have Boyle's law. If you hold these two constant, you have Charles' law. And if you hold these two constant, you have Avogadro's law. So that's why the combined gas law is so useful. If you vary all of them, you can still solve it. It's just that it has to be, the information has to be given in such a way that only one unknown exists. With one unknown, you can solve it. If there are two or more unknowns, you can't solve it. Not with a single equation. With a state function, which one do you use? The ideal gas equation. And for that one, you need to know what the units are. Pressures in atmospheres, volume in liters, moles, and Kelvin. With those units of measure, then you know what R equals. That's the trick. Which R do you use? Use the one that has these units in it.
So far, that's the only one that's on the whole board, I think.
Yep. Except for, wait a minute.
I've only worked halfway through.
So. Okay, the last one's where we get into Graham's law. It uses the other one. 8.3. See, I don't get it right. Since I don't use it every day. Yeah, 3145. I was right the first time. 1, 4, 5. Now the units of measure for this one, and this one right here, you're going to use that. Right. But on occasion, we'll use this one, which is joules per mole K. And for us, that has to do with Graham's law. Not Graham's. Not Graham's. Or maybe it is Graham's. I don't name that one. It's the one where you use your finding molar mass from. No. Now Graham's law you can do without it because the R factors out. But if you're determining average root mean square velocity, that formula, which I've lost over here. Welcome to Camp Foggy Brain. Back to you over again. That's where you need this one. If you're trying to determine the root mean square velocity for a gas at a given temperature, you would use the R value here for here. Okay? For now, Graham's law, you don't need it at all. Because Graham's law, the ratio in Graham's law factors out the R. It just disappears. So it doesn't matter which one you use. But for this one, if you have a question on that one, then that formula is in useful information. It's for calculating the velocity, root mean square velocity for a gas at a given temperature, and of a particular molecular weight or molar mass. Okay. But for all others, we'll use this one. Oh, I started on 30, just kind of veered off the path. A sample of oxygen has a volume of, okay, so we're going to extract information, 1.72 liters, and a temperature of 27 degrees C. So we know we're going to have to convert that one. It's 300. Okay. And what else are we given? Pressure. 800 torr. Okay. How many molecules does it contain? Right, so which kind of problem is this? Is this before or after a state function? Yeah, 50-50 chance, right? Now, if you look at the information, it's just given, what is it? One, it's given volume, temperature, pressure. It doesn't show two volumes or two pressures or two temperatures. It doesn't say anything's changed. It's just what it is right now. That's a state function. Okay? So, if the question is, how many oxygen molecules? What we're actually asking is that. Once you find the moles, then you can find the number of molecules. But for the gas equation, moles is your go-to. So with these four, we can solve it. We just have to solve for moles. And so this one stays put. These two go over there. Like that. Then we can plug in our values. Pressure is in liters. That's right. Because our R is in liter atmospheres per mole K. So we need the liter volume, which is true. And then pressure, 800 torr. All right, we got to convert that. It has to be atmospheres. So how do you convert it? Divide by 760. Okay, there's atmospheres. And then we have R and temperature, 300. All right, so now we'll find out how many moles first. I get 7.35, let's see. just need to find out how many molecules there is. What's the conversion for moles to molecules? How many molecules in a mole? How many chickens in a mole?
Is it, oh, Avogadro.
Yeah. It's 1022 times 10 to the 23rd. How's that number? And I get 4.43 times 10 to the 22nd molecule. Let's see if that's one of the answers. Yep, A. Are we good? I need to back up. Sometimes I wonder if it's making a connection.
Yeah, the 1.72 liters, why is it in the pressure part of the equation? Like where it's PV over RT? Okay.
I just
Thank
reversed them
you.
in my head. Sorry.
All right, well, that confused
I didn't put them in order.
me. Yeah, see, like little things like that, right? But it makes sense.
Okay, so let's, oh, we only got 5 more minutes. Gotta go in the lab. All right, I'm gonna try to pick out look at our choices, see which one had the greatest impact. Let's do a stoichiometry problem. Let's see, what's this one?
I think I know what you did on the balloons, where you had neon and whatever it was as mold. Should they have been grams to begin with, and then when you did the conversion, that way, if it was in grams, the grams would be on bottom, the mold would have been on top, and then
No, because
that wouldn't work.
that's where we were headed. We were headed for grams. We hadn't determined grams yet.
Oh,
I hadn't figured that one out either. I think that the explanation that we ended up on was the best way to look at it.
no.
Okay. 73 says calcium hydride combines with water according to the equation. Yeah. Beginning with 84 grams of calcium hydride and 42 water, what volume of hydrogen will be produced at 273 K and pressure of 1327 torr? Okay, this is a complicated problem. So we need to break it down. First of all, we're operating with a balanced equation. It's already given to you as balanced. Calcium hydride, solid, plus water, yields hydrogen gas and calcium hydroxide. Okay. Beginning with 84 grams of this. Okay. And 42 grams of that. What volume of this? So we want volume. The answers are all in liters. So we don't know how many liters of that are produced under what condition. So the conditions are 273 K 1327. Four. Okay. That's everything that's given. Okay, so let's work backwards. We know torr, and we're going to have to convert that to atmospheres. There's no way around it. Right, 1 torr is 1 millimeter of mercury, so the conversion factor is the same. And so we have so this is 1.746 atmospheres. Temperature's already there. So if we were to just sit here and look at this as our state, what are we missing? We've got this one. We've got pressure. The question is volume. So what we need is moles. We've got to find moles. How many moles of this are produced? Then we can solve it for volume, right? So the missing key, the missing piece to this puzzle is moles. So that brings us back over here. It's a stoichiometry problem. How many moles of H2 are produced? All right. Remember also when I said, when we were in stoichiometry before, when you're given absolute amounts of reactants, one of them is going to run out first. So we need to find the limiting reactant in this problem. Right? So what do we need? We've got to find moles of each. We can't go anywhere with grams. Right? So we got to find calcium hydride, molar mass, so that we can convert that to moles. So what's calcium hydride? Let's see, 4008 is calcium. Hydrogen is 1.01 each. So that's 2.02, right? So 4210 is that one, which divide 84. And I get mole of calcium hydride. Okay. How about water? Well, you know what water is, right? We've done it so many times. 18.02. 16 plus 2.02. So this one converts like that. So I get 2.3307 moles of water. Now, what do we do? Well, to find out the limiting one, you say, what if all of this is converted to hydrogen? So you make the conversion. There's a 1-to-2 ratio. Yes. Right. So coefficient there is 1, there's 2. So we actually have 2 times that. It's still, yeah, it's still in here. So we get 3.9905 moles of hydrogen. Okay. What if then all of this is converted to hydrogen? What's the ratio there? This is your conversion factor. It comes straight out of the equation. 2 to 2, which is 1 to 1. Okay, now which is the least? This one. Right? That one's bigger than this one. This is the limiting factor. So this conversion yields only that amount of hydrogen, the smaller amount. Now we've got our moles. We can solve for volume. So volume equals nRT over P. Number of moles, I'll try to put them in order this time. 0.08206, and temperature is 273, divided by pressure, 1.746. And now it's just crunching numbers. So I get 29.9. Let's see, is that one of the answers? Yep, it's A. Okay. Well, we didn't get to everything. Fortunately, I have recordings from the last time I taught this course, last semester. It's also in there. So once you get through looking at this one, if you want to go back and review this one, then and go to the other recording and see if there's anything different in it. Or if you get stumped on a problem, just call me, text me or something, and we'll try to figure it out.
So when you're doing this, you always use the limiting, right?
Yeah, if you have absolute amounts of the reactants, one of them is going to run out. If you're only given one of them, you have to assume that you got plenty of the other, and you base your calculations on the one that's given. But if you have two or more, if there are three reactants, if two of them are given, then one of them is going to run out. So you just find out, what if you use all of one? What if you use all of the other? And the least one is your limiting. It produces the least amount of product. It has to be the limiting one. So this is sort of the next step. Stoichiometry problem using gases. Okay, so I guess it's time to head to the lab. Since there's only three of us, we'll probably just, I got 3 stations set up in there. So you can split if you want, right? If you want to have more hands-on, you can split into 2 groups. Everybody needs to have a partner, so at most we'll have 2 groups today. And let me shut this off. Stop the